So let's take a look at graphs networks because they're used to study topologies. So complex data has an underlying topology, and usually that underlying topology can be modeled by a complex network. Now these are simple networks, and they may be very large, high order, many vertices, but they don't necessarily mean they're complex. So simple networks imply simple topologies. So if I took a graph and drew it on a surface without any edges crossing, then the genus of the graph is the surface with the lowest genus on which that graph can be drawn. Genus is the number of holes in a surface. So for example, a planar graph can be drawn in the plane without any edges crossing. And that corresponds to drawing on a sphere which has genus 0. There are no holes in a sphere. I can take some graphs, they may not look planar, but we can redraw them so that they are planar. Here's a graph, and it actually is planar, but I'm going to leave it to you to figure out how to make it planar. A torus graph is more complex than a planar graph because we can draw it on a torus, but not on a sphere. Here's the same graph redrawn and redrawn again, and you can see the toroidal structure implied there. A torus has a hole, it has genus 1. These are real-world networks. They're large order, but they also tend to have a complex structure, maybe corresponding to a high genus. And there are other important properties for real-world networks. They tend to grow. So recall the definition of degree of a vertex. In real-world networks, the larger the degree of a vertex, the faster it tends to add neighbors. This is called the rich get richer. A few of the many vertices, therefore, will end up with very high degree. But most of the vertices in real-world networks start at a low degree, and they tend to remain at a low degree. So we look at what's called a degree distribution, which is a function that counts the number of vertices at a given degree. So degree here is an independent variable, and the count is dependent. And so we get these histograms. So we have here a little under 7,000 vertices that are degree 1, whereas there are fewer than 1,000 that have degree 6, as you can see here. Scale-free networks are when you have a degree distribution for a real-world network of a special type. They have vertices with lower degrees, and that's the most of the vertices, but a few that have very high degree. So a graph is defined to be scale-free if its degree distribution is a power law, or at least asymptotically is a power law. So a power law is just a function defined by the variable to a power, in this case a negative power. And here c is constant and the power p is constant. So we get this distribution model. So a power law distribution defines a scale-free network, and I can often use points instead of bars. So I'm looking at points on the curve rather than at a histogram. And if I do that, then I can take logarithms and end up with the logarithm of the count is the logarithm of a constant minus p times the logarithm of the degree. That means that the log-log plot of a power law is a straight line. So if I use log scale on both axes, a power law gives me a straight line, as you can see here. Now the total count is the sum of all the counts, the number of actual vertices. And if I take the individual counts and divide by the total count, I get frequency instead of actual count. And that's just a rescaling of the axes, of the vertical axis. And it's the approximate probability that a vertex V chosen at random will have a degree of D. Now, real-world networks are often scale-free, and we tend to look at their power law distributions in log-log scale. For example, airline networks, the larger the node, the greater the number of daily flights. Also in the natural world, here are metabolic networks and gene regulatory networks. Metabolic networks, here is their distribution in log-log scale, approximately linear. Here's gene regulatory networks. They don't start out necessarily in power law, but you can see they asymptotically approach that straight line. Real-world networks also tend to be small world, highly clustered, but vertices still close to each other on average. The clustering coefficient of a vertex is simply the number of pairs of adjacent neighbors over the number of pairs of neighbors. Now, this is easy to illustrate. Take a vertex, find its neighbors, look at that subgraph. So there are 4 neighbors, and that means that there are this many pairs of vertices, 6. So the number of pairs of vertices is 6. And how many of these pairs are adjacent to, how many of these neighbors are adjacent to each other, ignoring the red actual vertex? Well, there's just 2. So this is the clustering coefficient of that vertex. If I have this vertex, graph, then here's a hub, so to speak, and notice I have all these neighbors, and there's lots of neighbors now, lots of pairs of neighbors, 21 in fact, but only one adjacency. So there's its clustering coefficient. Another way to look at the clustering coefficient is to say the number of actual triangles over the number of possible triangles, where each triangle has to contain the original vertex. So here's 1, 2 triangles, but there are 6 triangles possible. Here is 1 triangle, but there are 21 triangles possible. Here we have a clustering coefficient of 0 because none of the neighbors are adjacent to each other. The clustering coefficient of an entire graph is just the average of the clustering coefficient of its vertices. And notice this is between 0 and 1 because we're dividing by the total number of vertices. If it's approximately 1, then the graph is highly clustered on average. If it's close to 0, the graph is not highly clustered on average. It's low clustering. So let's look at this for what's called a random graph. You take n vertices, n here is large, and with probability p, any 2 vertices chosen at random are adjacent. But that means that the average degree of a vertex is p, that probability, times n. In other words, it's the percentage of n total vertices. So that means the clustering coefficient is p, which is just k over n. And that's approximately 0 because, remember, we said n here is extremely large. So the clustering coefficient of a random graph is close to 0. Now let's look at another concept of path length. So if I have 2 vertices in a graph, then I have paths between the vertices. The shortest path is the distance between the vertices. So here's a path of length 4. Here's one of length 4. There's one of length 7, but that one is length 3. And so that's the shortest path, and that's the path length, which we denote by DUV, the distance from U to V. The average path length is just the average overall pairs of vertices of the distances between the vertices. And if there is no, if the U and the V are the same, you just define the distance to be 0. So here we have these distances, and we have the path length. The average path length here is 4/3. Here, the average path length is 5/3. And there's a pattern here. I'll let you think about it. Here we have average path length of 1, here an average path length of 2, here an average path length of 3. And again, there's a pattern here. Notice that the average path length has to be greater than or equal to 1, but it could be huge. So the small world phenomena is that many real world graphs on average are highly clustered, tend to have short path lengths. In other words, 6 degrees of separation is what this phenomena is called. So a graph is small world if both the clustering coefficient of the graph is close to 1 and the average path length is close to 1 relative to the size of the graph. For instance, an airline network has a short average path length. In other words, you need at most 2 or 3 flights to get to your destination. It's highly clustered because most of the flights are out of only a few hubs. Gene regulatory networks, again, the average path length is small, but the clustering coefficient is large because it's related to the cellular response. Facebook, there's about 1 billion Facebook users. About 70 billion friendship links form edges. And by the way, we could do the same kind of analysis for Twitter, and this is also from 2019. The average shortest path length for Facebook, at least in 2019, is 4. That means you and a randomly chosen other user, a friend of your friend knows a friend of their friend. So you and them each have friends who have a common friend. 4 degrees of separation. But high clustering coefficient because Facebook tends to be formed by communities, a highly connected hub, and communities tend to attract members of other communities, forming even bigger communities. But here's the catch. Graphs produced by algorithms for k-nearest neighbors and for clustering and so on are rarely small world or scale free. So complex networks tend to be scale-free graphs that grow by adding edges much faster than they add vertices. Communities of communities of communities. And they maintain low average path length when they do that. Here we have a graph where the way I've connected these communities means that some vertices are very far apart. That's not real world. Real world, we tend to have communities of communities of communities. But KNN graphs tend to look more like random graphs. So we have n vertices. Any 2 chosen at random has probability p that they're adjacent. Each vertex in a random graph has about the same degree, as do k-nearest neighbor networks. But scale-free networks never have that property. So we've seen before the expected degree of a random graph is k. Not all networks are scale-free. For instance, the highway system tends to be an exponential network. Why? Because you really want it to be close to a planar graph. Most vertices in an exponential network have about the same degree. This is not a small world scale-free network. Random graphs, if p is small, is a bunch of disconnected components, and if it's large, tends to be very highly connected. So k-nearest neighbor graphs are very useful and they're very widely used. They usually, however, are only a superficial approximation of the complex topology of a set of big data. They often are not complex themselves. They often are not small world and not scale free. But real world networks tend to be complex networks that are small world and are scale free. So when we're using K&N graphs, we have to remember that they are not real world in general. Got to be careful. And yet, nearest neighbor graphs are still very useful.